So thanks to the organizing committee, because I'm sort of an outlier, and as a DA person, I could have easily been excluded as being on the tail of the distribution. I want to talk a little bit about some new methods we've been doing in the Data Assimilation Research Testbed, which we build and maintain at NCAR. So DART is a community data assimilation facility. It focuses on research and testbed. It is open source and open development, so we've had people from outside our group develop model interfaces, observation forward operators, and even assimilation algorithms, but it is purely an ensemble facility. DART works with more than 50 models. This is a subset of some of them across the Earth system. Today I'm going to talk about some results in 3 NCAR-based atmospheric models, CAM, CAM-CHEM, and WACM-X. WACM-X is a space weather model. In one of the online meetings of this organization during the pandemic, my colleague Kevin Rader talked about a reanalysis that was made with the CAM-6 model and using DART, and that was for 10 years. That data is now available from NCAR. The model in that reanalysis was a release that was used for CMIP6 of the CAM model at 1 degree with 32 levels, so this is a toy compared to the operational things we've been hearing about, but still a useful and moderately realistic toy. It carries along a land model, SST is specified, and sea ice coverage, etc., and aerosol and other forcings are specified. The assimilation uses a particular linear Gaussian filter, the Ensemble Adjustment Kalman filter, with 80 members and a 6-hour window, and some inflation and localization tools. And the observations assimilated here, limited remote sensing, but in situ temperatures and winds, cloud motion vectors, GPS occultation, and errors. So much more limited set, again, than most of the people we've seen here. Everybody knows what these observations look like in this crowd. And just to give you an example of what these things look like, this is a 500 hectopascal height field at a particular time. 20 of the 80 members are shown, and in black on top of those 80 members is the NCEP final analysis. So this system agrees well with a state-of-the-art, at that time, assimilation system where there's lots of observations available. In places where there are not observations available or information available, like heights in the tropics, there's a lot of uncertainty. So I quickly want to talk now, the algorithms that we use for ensemble data assimilation are extremely simple. Okay, high school students can work with these. I'll do a poor job explaining, but let me try quickly. So the methods we use, we make a forecast ensemble to a time tk plus 1. In this case, I'm showing 3 ensemble members. And at that time, we're going to assimilate observations, and we assimilate them sequentially, one at a time. All I have to think about is one observation for this method. I compute a forward operator, and I get a scalar problem at the top of this slide. I get information from this observation, the value and its likelihood. I do an implementation of Bayes in 1 dimension to get increments shown in blue for this prior there. And then I update all my state variables one at a time by simply doing linear regression with my prior ensemble statistics of those increments onto the state variables. So at the end of the day, I can do a fully implemented ensemble system with only thinking about a bivariate problem. Scalar problem for observation, bivariate regression to get the updates for everything else. And when I'm done with all the observations at this time, one after another, then I move on to the next time. It really works. It's, by the way, identical to much more complicated matrix implementations. Now, ensemble Kalman filters fit normal distributions when they're doing this step in the observation space. Okay, but at this point, we have now the capability to implement a nearly general solution in DART for that scalar problem. And let me show an example of why that might be useful. So let's say here in this schematic, I have an ensemble forecast, just 10 members shown here of temperature, and there's on the upper line there. And I have an observation with a likelihood in the red. The way these filters work, and this is what ensemble Kalman filters of all kinds do, sometimes it's hidden in the implementation. I fit a normal distribution to that ensemble. I use Bayes, which tells me to take the product of that prior and the observation to get a posterior continuous shown in blue. And then I need to select updated ensemble members. And it turns out the way to do this for deterministic filters that have been around for about 20 years is to conserve the quantiles. So the quantiles, the position in the distribution of the green prior ensembles, is the same as their position in the blue posterior. So this is all well and good if I'm doing temperature here, there's no problems. But suppose that I'm really doing ozone concentration. So all those negative values in the posterior there are something I'm not really happy about. So as I said, now we are capable of fitting any class any type of distribution to the priors. Here's an example showing fit in a gamma distribution, which is bounded below, and this might be appropriate for distributions of something like ozone. I can then take the products with bays in the same way and conserve the quantiles in the posterior distribution, which is now bounded below at 0. And now I get an update that is more consistent with what I want to do. As I said, we can do any family of distributions. The problem is, in many cases, we don't know what the right family of distributions is. And so in that case, we have a non-parametric distribution called the bounded normal rank histogram distribution, which works automatically. You just say, I don't know what the distribution is, please do something for me. All you have to do is tell it the bounds in this case, and it once again gives you a nicely bounded distribution. Okay, so that's great. That was for the top part of this where I'm doing a scalar problem, but then I still have to regress these increments onto the state variables, and it turns out using linear regression is a mess. So all that work I do can be wiped out by the linear regression. So on the left here I show a prior bivariate distribution. I've observed the horizontal variable, which is temperature. The vertical distribution is for an unobserved variable that's ozone, it's bounded below. And so if I do a nice normal distribution for the temperature and then I regress those, I get the blue posterior on the right. It is completely inconsistent with the continuous distribution, and it has a whole bunch of negative members again. So it turns out that we can modify this regression step to work in a transformed space. This is a specific type of Gaussian anamorphosis for those of you who are experts in the room. But the bottom line is by transforming the space, we can guarantee the boundedness of our distributions across all the state variables. And we now get a posterior that looks like the one on the right, where the cyan things are consistent with the distribution, and by definition, none of them can violate the bound. Okay, so quickly, we applied these new methods to the same reanalysis that we did with the EAKF at the last meeting. This is just showing fits to observations for a bunch of different types of observations in the northern hemisphere tropics and southern hemisphere here. And quite surprisingly to me, almost all of them are better. Blue means better for the new method. This was surprising because the free troposphere, with the types of observations we have, was not expected to be very non-Gaussian or very nonlinear. And yet these non-Gaussian nonlinear methods, which sacrifice the safety of assuming Gaussianity and linearity, still do better. So we've also applied this in a number of other reanalyses. I've said this one was work done by Ben Gobert, and here he's going to work in a chemical model. He's assimilating Moppet CO observations. The atmospheric part, the dynamical part of the model, is the same as I showed you in the previous examples. Okay, so it's the same as that reanalysis. But then in addition, he's adding in the Mozart gas phase chemistry and aerosol scheme, and he is putting in source estimations for gases and aerosols. This is with a 30-member ensemble for cost reasons for him. So he feeds all the state variables plus the sources. DART does its stuff with these new algorithms. It updates both the state variables in the traditional way and the carbon monoxide concentrations and the anthropogenic and fire emissions. I'm just going to quickly show you here. Again, he's done this with both the traditional ensemble adjustment Kalman filters, which are a Kalman linear Gaussian filter, and the new methods. The key plots here are, this is on the left, this is the control, which has no Moppet observations. The middle one is assimilating Moppet with the EAKF, and the panel C is assimilating with these new methods. If you look at the RMSEs, they're about the same. As you go across this, 21 for the control, down to 13 for Moppet, and then an additional decrease in RMSE to 11.8. The right panel is fits again. These are fits to 143 observation sites from the NDACC network, by the way. Again, you're looking at the RMSE on the right, and again, this is percentage of reduction. At the end of the day, the RMSE with the linear Gaussian filter is 8.58 parts per billion, and it's down to 7.7 parts per billion with the new filters. This is one more look at this. In this particular case, we're looking at actual fits to the forecast Moppet CO retrieval concentrations. The top panel is when you're not assimilating any Moppet. The middle panel is when you're assimilating using the EAKF, the linear Gaussian method. The bottom panel is when you're assimilating using the new non-Gaussian, non-linear methods. And what you see here is, of course, there's a significant reduction in the errors of the fits when you actually add in the assimilation of the Moppet. But then there's an additional correction that comes in with the nonlinear algorithms. Again, we still expect these fields to be fairly linear and Gaussian because we're not actually getting near to the bounds for carbon monoxide. Okay, so it's obviously bounded below as a tracer, but the atmospheric concentrations are not generally getting close to that bound. There are a number of other fields in the atmosphere that do get close to their bounds. Things like cloud ice, which can go away altogether in different places. Precipitation, which is a mixed bounded distribution. It can have lots of cases where it's all zeros, but then you have a continuous distribution in other ways. And these methods can actually deal with mixed, bounded, continuous, discrete distributions, any type of distribution that you want to try to put in. So in conclusion, there's a lot of reasons why the DA problems we're working on are nonlinear and non-Gaussian, and many of them have mixed distributions. That's where you have partly discrete. There's a 60% chance that there's going to be no more precipitation measured here in Tokyo this afternoon, and then the rest of it is some continuous distribution of some variable amounts that could happen. Parameters are much the same way. Many parameters have discrete values or may have bounds below. We've heard talks earlier about the need for parameter estimation to improve models. Sea, ice, snow, other things have bounded distributions for their concentration, sometimes bounded on both sides. So we now have a capability in DART to apply methods that can deal with all of these distributions. They deal with it exactly in the scalar observation space. They do not deal with it exactly, but they're a better approximation for the nonlinear relationships in the bivariate space of the regression. We've applied this to a number of large models. I didn't have time today to talk about the space weather in WACM-X, which is ground to space, where this is being used for coupled data assimilation. So far, all of the large applications, the results have been positive. The incremental cost is less than 10% compared to the base, and DART is heavily optimized, very fast parallelized code. All of this is public, of course. You can try it out at DART. And the reason I'm giving this talk is I know it takes a long, long time to move these types of things into any sort of operational system. Plus, we have the oddity of being an ensemble system like Lars. But I think there is potential to do a lot more than we've been doing so far by starting to play now with things that are not the easy, low-hanging fruit on observations and variables. And so thanks for your attention.